The topic for today's module is zero divisor and group of units. Dear learners, in this section we are going to discuss briefly about zero divisors and group of units. First, let us start with the definition of a zero divisor. Any element A in R is said to be a zero divisor if there exists a non-zero element B belongs to R such that AB equal to 0 or BA equal to 0. In any ring, certainly 0 is a zero divisor according to our definition. Next, let us see some examples of zero divisor. The first example is find all the zero divisor of Z15. The elements of the ring Z15 is set of all 0, 1, 2, 3, etc. up to 14. Here 3 dot circle 5 equal to 0, 6 dot circle 10 equal to 0, 9 dot circle 5 equal to 0, 12 dot circle 3 equal to 0. Here 0, 3, 5, 6, 9, 10 and 12 are zero divisors. The second example is find the zero divisors of R cross R. The elements of the ring R cross R equal to set of all ordered pair A comma B such that A in R and B in R. Ordered pair 1 comma 0 dot circle ordered pair 0 comma 1 equal to ordered pair 0 comma 0. The ordered pair 1 comma 0 and ordered pair 0 comma 1 are zero divisors. In fact, all the elements of the form ordered pair A comma 0 and ordered pair 0 comma A, where A not equal to 0 belongs to R, are zero divisors. Next, let us see the third example. In the ring of integers Z, no non-zero element is a zero divisor. The fourth example is the ring of integers modulo a prime number Zp has no zero divisors other than 0, since every non-zero element is a unit. This ring is a finite field. More generally, a division ring has no zero divisors except 0. Fifth example is find the zero divisor of Z6. Here 2 is a zero divisor because 2.3 is congruent to 0 mod 6. However, 5 is not a zero divisor on Z6 because the only solution to the equation 5x is congruent to 0 mod 6 is x is congruent to 0 mod 6. 1 is not a zero divisor in any ring. Let us start the next part of this module, which is units. We defined R star, Q star and C star by removing the 0 element from R, Q and C. Example is R star equal to set of all A in R such that A not equal to 0. We found that R star is a group with respect to multiplication. But we tried to do the same with Z and failed to obtain a group. Note that R, Q and C are rings and so is Z. Given a ring, is there a naturally defined subset that is a group with respect to multiplication? It turns out that the answer is yes, and that for R, Q and C we obtain R star, Q star and C star we would expect. To define this subset, we need the concept of a unit. So, let us recall the definition of a unit. Let R be a ring. An element U is called a unit if there is some element V in R such that UV equal to VU equal to 1. In other words, an element U of R is a unit if it has a multiplicative inverse that belongs to R. Let us see some examples. The first example is In any ring, 0 is a non-unit. Second example is in R, Q and C, every non-zero element has a multiplicative inverse. So, the units are the non-zero elements. Third example is, what are the units in Z? Suppose U is a unit in Z. Then there exists some V in Z such that UV equal to VU equal to 1. This means that 1 by U is an integer. The only integers U such that 1 by U is also an integer R plus or minus 1. So, the units in Z are plus or minus 1. Example 4 is, a ring R is a division ring if and only if U of R equal to R different singleton 0. In the ring Z by n is set of integers modulo n, the units are the congruence classes mod n represented by integers co-prime to n. They constitute the multiplicative group of integers modulo n. Sixth example is, any root of unity in a ring R is a unit. That is, if R power n equal to 1, then R power n minus 1 is a multiplicative inverse of R. Seventh example is, the unit group of the ring Mn of F of n by n matrices over a field F is the group G Ln of F of invertible matrices. Now, let us define the unit group. Let R be a ring. We define the unit group of R to be the U of R equal to set of all A in R such that A is a unit in R. Just because we have called U of R the unit group of R does not get us out of checking that it is really a group. So, let us verify the set of units U of R comma dot forms a group or not in the following theorem. Theorem statement is, let R comma plus comma dot be a ring. Then show that U of R is a group under multiplication. The proof of the theorem is, we must first show that U of R is closed under multiplication. Suppose U1 and U2 belongs to U of R. Since U1 and U2 are units of R, and so there are V1 and V2 are also in R such that U1 V1 equal to V1 U1 equal to 1 and U2 V2 equal to V2 U2 equal to 1. We want to show that U1 U2 is a unit. Note that V1 V2 belongs to R. Since R is closed under multiplication, it is a ring after all. Moreover, we have U1 U2 into V2 V1 equal to U1 into U2 V2 into V1 by associativity of multiplication. That is equal to U1 into 1 into V1 since U2 V2 equal to 1. That is equal to 1 since U1 V1 equal to 1. Similarly, V2 V1 into U1 U2 equal to 1. Thus, U1 U2 into V2 V1 equal to V2 V1 into U1 U2 equal to 1. And so, U1 U2 is a unit in R. Therefore, U1 U2 belongs to U of R. We have proved that U of R is closed under multiplication. Next, we want to show that multiplication is associative in U of R. But multiplication is associative in R since R is a ring. Therefore, it is associative in U of R since 1 into 1 equal to 1. Therefore, 1 is a unit and so 1 belongs to U of R. Finally, we want to show that every element in R star has a multiplicative inverse that belongs to U of R. Suppose U belongs to U of R, then UV equal to VU equal to 1 for some V in R. Note that This makes V also a unit, and so V in U of R. Thus, U has a multiplicative inverse in U of R. Hence, U of R is a group under multiplication. Hence, we proved. Now, we look into some examples. The first example is, find the group of units in Z14 and prove that U of 14 is a group under multiplication. Construct a multiplication table for U of 14. U of 14 consists of the elements of Z14 which are relatively prime to 14. Thus, U of 14 equal to set of all 1, 3, 5, 9, 11 and 13. You multiply elements of U of 14 by multiplying as if they were integers, then reducing mod 14. For example, 11 into 13 equal to 143. When we divide 143 by 14, the remainder is 3. So, it can be written as 3 mod 14. So, 11 into 13 equal to 3 in Z14. Now, we construct the Cayley table for U of 14. Here the operation star is the multiplication modulo 14. The elements in U of 14 are 1, 3, 5, 9, 11 and 13. Here we write it in the first column and in the first row. Now, we multiply the elements. 1 star 1 is 1, 1 star 3 is 3, 1 star 5 is 5 and 1 star 9 is 9. 1 star 11 is 11 and 1 star 13 is 13. Similarly, we multiply the first column also. Next, we multiply 3 star 1, 3 star 1 is 3, 3 star 3 is 9, 3 star 5 is 15. When we divide it by 14, we get the remainder is 1. So, the answer is 1. Now, we multiply 3 star 9, 3 star 9 is 27. When we multiply it by 14, the remainder is 13. So, the answer is 13. Similarly, 3 star 11 is 5, 3 star 13 is 11, 5 star 3 is 1, 5 star 5 is 11, 5 star 9 is 3, 5 star 11 is 13, 5 star 13 is 9, 9 star 5 is 3, 9 star 9 is 11, 9 star 11 is 1, 9 star 13 is 5. 11 star 3 is 5, 11 star 5 is 13, 11 star 9 is 1, 11 star 11 is 9, 11 star 13 is 3, 13 star 1 is 13, 13 star 3 is 11, 13 star 5 is 9, 13 star 9 is 5, 13 star 11 is 3 and 13 star 13 is 1. Notice that the table is symmetric about the main diagonal. Multiplication mod 14 is commutative and U of 14 is an abelian group. The second example is, find the group of units in ZP where P is a prime and prove that U of P is a group under multiplication modulo P. If P is prime, then all the positive integers smaller than P are relatively prime to P. Thus, U of P equal to set of all 1, 2, 3, 4, etc. up to P minus 1. For example, in Z11, the group of units is U of 11 equal to set of all 1, 2, 3, 4, etc. up to 10. Construct a multiplication table for U of 11. The operation in U of 11 is multiplication modulo 11. For example, 8 into 6 equal to 4 in Z11. As we construct the Cayley table for U of 14, we can construct the Cayley table for U of 11 as follows. From the table, U of 11 is an abelian group and so U of P form an abelian group where P is a prime number. Now, let us see some basic properties of zero divisor and units of rings. First property is any unit in R cannot be a zero divisor. Proof of the property is, let A in R be a unit. Suppose AB equal to 0. Now we are going to multiply A inverse both sides. We get A inverse into AB equal to A inverse into 0. By using the associative property, it can be written as A inverse A into B equal to 0. Therefore, we get B equal to 0. Similarly, if BA equal to 0, then B equal to 0. Thus, A cannot be a zero divisor. Note that A is not a zero divisor does not imply A is a unit. Second property is, a ring R has no zero divisor if and only if multiplication cancellation law is valid in R. Proof of the property is, let R be a ring without zero divisors. Let Ax equal to Ay with A not equal to 0. Therefore, Ax minus Ay equal to 0. This implies that A into x minus y equal to 0 and A is not equal to 0. Since R has no zero divisors, we have x minus y equal to 0. Then x equal to y. Thus, cancellation laws are valid in R. Conversely, let the cancellation law be valid in R. Let AB equal to 0 and A not equal to 0. Then AB equal to 0 equal to A into 0. That is, AB equal to A into 0. So, by cancellation law, we get B equal to 0. Therefore, R has no zero divisors. Third property is, a field has no non-zero zero divisor. Proof is, seeking a contradiction, suppose that X is a non-zero zero divisor of the field F. This means that there exists a non-zero element y in F such that Yx equal to 0. Since y is a non-zero element in F, we have the inverse y inverse in F. Hence, we have 0 equal to y inverse into 0, that is equal to y inverse into Yx, since Yx equal to 0. By associativity, it can be written as y inverse y into x. Since y inverse y equal to 1, that answer is 1. This is a contradiction because x is a non-zero element. We conclude that the field F does not have a non-zero zero divisor. Fourth property is, if AB equal to 1 in a ring R, then BA equal to 1 when A or B is not a zero divisor. Proof is, an element x in R is called a zero divisor if there exists a non-zero element y in R such that xy equal to 0 or yx equal to 0. So, if x is not a zero divisor, then xy equal to 0 implies that y equal to 0. Similarly, yx equal to 0 implies that y equal to 0. First, to prove that if A is not a zero divisor, then BA equal to 1. Suppose that A is not a zero divisor. We compute A into BA minus 1 by distributivity. A into BA minus 1 can be written as ABA minus A. Since AB equal to 1, it is equal to 1 into A minus A, that is equal to A minus A equal to 0. Since A is not a zero divisor, this yields that BA minus 1 equal to 0 and hence BA equal to 1. Next, to prove that if B is not a zero divisor, then BA equal to 1. Suppose that B is not a zero divisor. We calculate BA minus 1 into B. By distributivity, BA minus 1 into B can be written as BAB minus B. Using AB equal to 1, it can be written as b into 1 minus b, that is equal to b minus b equal to 0. Therefore, ba minus 1 into b equal to 0. As b is not a zero divisor, the equality ba minus 1 into b equal to 0 implies that ba minus 1 equal to 0. Hence, we have ba equal to 1. Next, we are going to see some properties without proof. The first property is, in the ring of n by n matrices over a field, the left and right zero divisors coincide. They are precisely the singular matrices. In the ring of n by n matrices over an integral domain, the zero divisors are precisely the matrices with determinant 0. Second property is, a non-zero commutative ring whose only zero divisors are 0 is called an integral domain. The third property is, in an integral domain, the cardinality of an equivalence class of associates is the same as that of U of R. Let us see some concepts related to associates. First, we are going to see the definition. If A and B in R, then D in R is said to be a greatest common divisor of A and B if D divides A and D divides B, and whenever C divides A, C divides B, then C divides D. We shall use the notation D equal to A comma B to denote that D is a greatest common divisor of A and B. Let R be a commutative ring with unit element. Two elements A and B in R are said to be associates if B equal to UA for some unit U in R. The relation of being associates is an equivalence relation. Note that in a Euclidean ring, any two greatest common divisors of two given elements are associates. Some results are as follows. The first result is, let R be an integral domain with unit element, and suppose that for A and B in R, both A divides B and B divides A are true. Then A equal to UB, where U is a unit in R. Proof of the result is, let R be an integral domain. Then R has no zero divisors. Since A divides B, we have B equal to x into A for some x in R. Since B divides A, we have A equal to y into B for some y in R. We have B equal to x into yb. In the place of A, we put yb. By using the associativity, it can be written as xy into b. But these are the elements of an integral domain, so that we can cancel the b and obtain that xy equal to 1. Y is thus a unit in R and A equal to yb. Hence, we proved. The second result is, let R be a Euclidean ring and A and B in R. If B is not equal to 0, is not a unit in R, then D of A less than D of AB. Proof is, let R be an Euclidean domain. Then R satisfies the following conditions. The first condition is, for A comma B not equal to 0 in R, then D of AB greater than or equal to D of A, which we taken as equation number 1. If A and B in R and B not equal to 0, we can write A equal to BQ plus R with Q and R are in R such that A either R equal to 0 or D of R less than D of B, which we taken as equation number 2. Consider the ideal A equal to ideal generated by A, that is equal to set of all XA such that X in R of R. By equation 1, we have D of A less than or equal to D of XA for X not equal to 0 in R. Thus, the D value of A is the minimum for the D value of any element in A. Now, AB belongs to A if D of AB equal to D of A. Since the D value of AB is minimal in regard to A, every element in A is a multiple of AB. In particular, since A in A must be a multiple of AB, whence A equal to AB into X for some X in R. Since all this is taking place in an integral domain, we obtain that Bx equal to 1. In this way, B is a unit in R, in contradiction to the fact that it was not a unit. Thus, D of A less than D of AB, hence proved. Now, we are in the end of this session. So, let us recall the concepts once again. First, we have started this session by describing about zero divisors and units with some examples. After that, we had proved that the set of unit forms a group. Moreover, we had discussed as many as examples for your understanding. Finally, we conclude this session with discussing some results based on associates and Euclidean domain. I hope this is useful for you. Thank you.